MS Ramaiah University of Applied Sciences.
Hello students, in this session of control system MATLAB videos, we are going to study how to plot a Nyquist plot. First, open a new script. So in this editor window, we are going to type the program. First, let us clear the command window by the command clc. Next, we'll clear all the memory using clear all. First, let us define the variable s using the command syms space s. Now, let us define the numerator num is equal to sym to poli of. Here we will type our transfer function numerator. So the numerator is 0.5s plus 1 into s plus 1. So this is the numerator, 0.5s plus 1 into s plus 1. The denominator is sym to poli of. Here we will enter the transfer function denominator, which is 10s plus 1 into s minus 1. S plus 1 into s minus 1. Let us now define the transfer function gh as transfer function of numerator comma denominator num comma den. Let me save this. I give the name Nyquist plot. Save. Now run the script. So this is the transfer function, 0.5s square plus 1.5s plus 1 divided by 10s square minus 9s minus 1. And these are the coefficients of the numerator and the denominator. Now let me enter a gain factor called k. I give the value as 1. Now let me insert this in the transfer function. So since it is in the forward path of the transfer function, I write it as k into numerator comma denominator, and I get the same transfer function as k is 1. Now let us plot the Nyquist plot by entering the command nyquist of the transfer function gh. Okay, run the script and you get a plot of the Nyquist diagram. So this is the Nyquist plot for the given transfer function. So as you can see, the Nyquist plot does not encircle minus 1. So it does not encircle minus 1, instead it just passes through minus 1. So as you can see in the denominator, I have s minus 1 into 10s plus 1. one pole on the right hand side. So therefore the system is unstable. So let me increase the value of k and see what happens to the Nyquist plot. Right click and select increment value and run selection. So as I press on plus, the value of k is increased and the script is run and we get a new plot. So here you see that the -1 is encircled by the Nyquist plot in anti-clockwise direction. It is in anti-clockwise direction. Now, for the system to be stable, the number of encirclements should be equal to the number of right half poles in anti-clockwise direction. Therefore, let me define M as a closed loop feedback system which is GH, 1. This is the closed loop transfer function, and let me find out the step response for this transfer function. M is a closed loop transfer function. GH is the open loop transfer function. So remember that the Nyquist plot is always plotted for the open loop transfer function, and through that we can find out the stability of the closed loop transfer function. So now if the step response is bounded, then it means that the system is stable. As you see here in the step response, the amplitude of the step response goes on increasing, therefore the system is unstable. So according to Nyquist plot, the number of clockwise encirclements around -1 should be equal to number of right hand poles. So as you can see, -1 is still encircled in anti-clockwise direction, not in clockwise direction, therefore the system is still unstable. Let me increase the value of k again to see whether the system is stable. You see that -1 is shifted more towards the right, and the step response is also moving towards stability, but it is not stable yet. Now let me increase the value of k further and see that -1 has moved more towards the right, or the plot has moved more towards the left, and the system is still unstable. Let me increase further. Now -1 is exactly in between the two lobes of the Nyquist diagram, so therefore the system is having a sustained oscillation, or the system is critically stable. So you see sustained oscillations, therefore the system is critically stable. Let me increase the value of k further, and you see that the value -1 is encircled in clockwise direction once, therefore the step response also appears to be stable. So now if I further increase the value of k, -1 further moves into the smaller lobe and therefore the stability of the system also increases. So as you see, the stability of the system has increased. So that is how we find out the gain for which the system is stable using the Nyquist plot. Now I'll increase the gain further and you see the system becomes more and more stable. So that is how you find out the gain K for which the system is stable using the Nyquist plot. I will further increase the value of K. That is, the system is stable for K greater than 6, as we saw earlier. Any value of K more than 6 makes the system stable. Thank you.
At MSR UAS, we spark your imagination unlike any other.